So let's just continue our discussion on finding ways of making a distortionless transmission system. So we've modeled our general communication system as a LTI system, and just looking at it in the frequency domain, we have an input and we have an output. And ideally, we want the input and the output to be very similar or the same in most cases. So we want some kind of transfer function for the full communication system that does not modify the input signal. So this would be a distortionless transmission when we have the input signal totally unmodified by the communication channel. So we have minimal effect from the transfer function of this general communication system. So if we were to do this, we would say that we want the input signal to be the same as the output. We would say that the only change that would be allowed would be some kind of time delay. So we have the same signal, just delayed in time. And I'll add in one more note that the amplitude may change, but only if the components across all frequencies are changed by the same amount. And that would give us a distortionless transmission system. So in equation form, we could say what this means is that we desire our output in the time domain to be the input message X, just changed by some time delay, and just modified by some constant coefficient. So in order to obtain distortionless transmission, these would be the only two things allowed: some constant modifier to the time domain input signal, and some constant time delay to this input signal. These would be the only things allowed in a distortionless transmission. So the K is a multiplicative constant, and the TD is a time delay. So if you recall the time shift property, which was discussed in previous chapters, right, we could convert our ideal time domain distortionless signal, we could convert it into a frequency domain signal, which may be a little bit easier to work with. And if we do that, we see that our output signal in the time domain would have some constant, multiplicative constant. And then based on this time shift property, right, we would have some time delay that's introduced by this constant time delay, and that would appear in this exponent here. Now, if you recall, in an LTI system, right, we could characterize the output in the frequency domain like this. And we will assume that our system is an LTI system. And so this means that our transfer function for the general communication channel would have this form. So if our transfer function has this form, and our ideal distortionless signal looks like this, what we are now interested in is seeing how can we look at this ideal time domain, this ideal frequency domain, and determine what the ideal transfer function would be. So which parts of this correspond to this transfer function? So this K would be the multiplicative constant K would be the amplitude response of the transfer function. So this is the amplitude response of our communication channel. So as our signal passes through all those digital analog converters, the channels, etc., what does the amplitude response look like? And then as the signal is sent at some time, and there's some delay as it passes through the channel, that delay is going to appear in this phase response. So this means that in our ideal distortionless transmission, we would have a transfer function that looks like this, or is characterized like this, where the amplitude response is constant, and the phase response has this form as seen here. So this is the form of the transfer function that's required for distortionless transmission. So if you want to have distortionless transmission, if you want to be able to take a message xt and pass it through some system and have an output y of t that's changed only in amplitude, only in constant amplitude, and only delayed by one time, then this is the form required for your distortionless transfer function.